Universal Time.
I am in radio contact.
Today in the lab, it is another RC-85 repeater controller by Advanced Computer Controls. This controller is special because it belongs to engineer Frank. Frank is a friend of the show, but more importantly, Frank actually worked for Advanced Computer Controls sometime in the late 80s, and my understanding is that he basically worked for them and got this controller in exchange for his efforts working there, as might have been an intern. I'm not exactly sure. But yeah, this one's a little bit sick. Frank said he was working on it and he thinks a wire got loose, possibly this one, and we noticed that one of the chips is blown up, actually has a crater mark in it, and has some other miscellaneous problems, so we are going to refurbish it and upgrade it for Frank. So here's what I was saying about the chip that actually exploded. You can actually see a crater in it and a part of the die, but yeah, good stuff. And we have some the wires soldered directly to the headers, which I hate, so we will replace those with new headers. Frank also reports that when he uses the normal power inlet connector that he gets an instant short, so I think that's going to be a good place to start taking a look. So in the later version of this board, these two diodes, which are Zener diodes, were added as voltage protection. Not exactly sure what the values are because they're not labeled on the schematic. Or, I mean, the values aren't on the schematic and there's no official parts list, but my guess is that someone overvoltaged these, which apparently, maybe. They're not showing up as a spark, so, oh, okay. So that one so CR11 is across the plus 12 input. Maybe we can try it on diode, but it's a Zener, it might not show up. Alright, so on diode it reads as 1.7 volts. And going back the other way, 0.599. Interesting. Then this one should be on the 5 volt rail, so this reads 0.7 volts going that way and 0.4 going that way. But we probably have to take them out of the circuit because the regulator is probably messing up those readings. Alright, so it turns out these are actually transient voltage suppression diodes. So this one here is the P6KE16A. Then this one is P6KE6.8A. So this one's 16 volts, this one is 6.8 volts. I might order these. Apparently these are still made. I did order Zener diodes, so I have a 16 volt and I was going to use a 5.6 volt on the 5 volt rail, but since I have to order a few parts from Mauser anyways, I'll probably put in just get new parts for these and get them coming. So on the back of the board I got weird corrosion going on the auto patch relay. I don't know what happened there. Up here doesn't look too good either. That's right. Sometimes you want to add a little bit of fresh solder just so it helps the old solder come out. That actually worked pretty good. Beauty. Alright, and with a little bit of coercion, we were able to get the auto patch relay out and check out this corrosion. I don't know, maybe this was replaced at some point in time? Or I don't know what would have caused that. But, yeah, nice. Unfortunately, it looks like some of the pads are a little bit gone, but we'll see what we can do to get this patched up. Haha. Also, it kind of looks like somebody soldered a wire to the ground plane here, but while they were at it, they messed up these two capacitors. So I'm going to get those out and get those replaced with some fresh new ones here in a bit. So after review, I think this is actually lightning damage on the auto patch relay, because I got craters in the board and char marks. So yeah, and the relay here has a 1989 date code on it, so I'm thinking it's the original relay, but probably hit by lightning at some point in time during its life. Like, the only other thing I would suspect is maybe somebody used like some sort of rosin that was like fully activated or corrosive and didn't clean it off after replacing the relay, but I'm just not sure what happened there. To determine if we've got any bad chips, I'm going to be testing them with the Chip Max 2, which is also the EEPROM programmer I prefer to use. So it actually has an IC test function, and you can load chips and test them. Okay, so I just noticed So the chip with the crater in it is branded by Harris, and then the chip next to it, which is also 74HC259, is branded Motorola. So it's possible that, I'm assuming that this Motorola chip would be the original, as the vast majority of the other chips on the board are Motorola, and this one must have been replaced at some point in time. Alright, select the 74259, load it. And we'll try the one that doesn't have the crater in it first and test it. And IC test is passed. Test this one. The one with the crater in it. And that one fails. Beauty. And there is a handful of chips that the Chip Max just can't test, so these are CD4053s, so they weren't on the list of known chips, but interestingly the 4051, which is very similar, was. So we'll just have to play it by ear as to whether these are bad or not. I might just replace them just because I've got a tube of 15. Alright, we've got our RC-85 wired into the Agilent E3611A variable power supply, so we can slowly bring up the voltage and see how we're doing. While you weren't looking, I replaced the voltage regulator with a new L7805CV. I also replaced the electrolytic capacitors on the board. These are solid electrolyte capacitors, so they'll never go bad again. So modern motherboards use these. So nice little upgrade, and they are better ESR wise because there's no liquid. Alright, turning the power supply on. 3.8. So with 4.5 in, I got 3.815 on the input of the regulator, and that's because we have a 1N4007 diode in series, so we're getting that 0.6 volts of drop. So on the output of the regulator, I show 0.894 right now, so I'm going to ramp up the voltage, and I'm watching current just to make sure I don't have like any kind of spikes. So at 6.5 volts, drawing 80 milliamps.
RC-85 V3.1.
Well, alright, and that happened at about 9 volts on the input.
RC-85 V3.1.
Alright, it's actually 9.6 volts. So after 9.6 volts, the unit comes out of reset. So with your nominal 13.8 volts, we are drawing 90 milliamps off of the supply. I have a solid, almost right dead smack at 5 volts on the output of my regulator. So the other thing I'm curious about is how the negative voltage generator is doing. So that's this section of the board here with the LM386. So let's see. There's a 79 L05 that comes off of that as well. So the 79 series has a different pinout than the 78 series, so just beware of that. That might be ground. Oh, so there's our negative 5 volt output. And 10.25 coming out of the negative voltage generator. And I don't know if it's the new capacitors or not, but I don't hear any high voltage or the normal 15 kilohertz whine that you have coming out of the negative voltage circuit on one of these controllers. Interesting. But yeah, I think we're more or less in business until the parts we have on order come in next week. Alright, parts are in. Let's see what we can do to clean up this trace that's under the auto patch relay. Kinda looks a bit nicked, but I don't know. Alright, I guess that ain't too bad at all then. So that should come up with some solder wick. It might be a bit nicked, I'm not sure. Yeah, there's a nick there. Alright, I'm going to add a little jumper that it's a little piece of wire off of a resistor to try to solve this nick that's in the trace here. I just want it a little bit beefy because this is the power. This trace goes between the plus 12 input and the TVS diode. And that looks good. Apply just a little bit of green solder mask here, try to clean up our work. Maybe fill in some of the other holes too. I'm just using a resistor lead because don't want to go through all the hassle of putting in a needle and trying to clean that up. Got us a little super weld, JB Weld ultraviolet curing crazy glue. Might not be strong enough, but yeah, that's what I got. Alright, let's get our new TVS's in here. The 16 volts goes into CR11. And the 6.8 volt goes into CR12, which, interestingly, that's on the 5 volt line, was the one we patched earlier. I thought that was the 12 volt main input. No, it's just some residual noise because I still have the audio amp hooked up. Alright, for the replacement auto patch relay, we are going with the Omron G5V-2-H1 12 volt coil version, which this should be the identical pinout and coil specifications. Frank expressed a desire to have the firmware upgraded to the latest, which is version 5.2, so I've burned that to a new 27C011 EEPROM. I have a factory default copy of the double EEPROM on a new 28C64. I have a Dallas DS1216 equivalent, our DS1216E equivalent clock sandwich that I have built. So this is, I designed it so you can actually change the battery instead of it being forever encapsulated in epoxy. And then as also part of the upgrade as an anti-piracy measure, I have a PAL Faker board. So between version 3 and version 4, they added a board with a PAL as part of a memory protection or a copy protection scheme, because I believe they were charging $150 to do the upgrade. So someone took a PAL board and figured out that really all they did was change the addresses of a couple of the major chips around, and basically this unscrambles the scrambling that was done in the software. Okay, so as it turns out, this version of the board actually does not need the PAL Faker because apparently it was made after 1987, and I guess they added those changes. So I'm thinking maybe it was between version 2 and version 3 of the firmware that they added the PAL needed for the copy protection, but it turns out, like I said, this version doesn't need it, and we put in the original 74 HC138, and it is running just fine.
RC-85 V5.2.
Okay, so one of the things that I didn't get around to before because I couldn't find the board was test the op amps. So this is an op amp tester, and we've got some LEDs here and reference LEDs based on a, I believe it's an NE5534. That's our reference chip. So this is like the speed control on this button. And on the 5534 we have enough speed to where we can get both LEDs lit, but that isn't really the case with the TLO64 here. But pretty much that tells us it's a good op amp. So I had a suspicion that we might have bad FETs on the board because of the chip that cratered next to them, so I pulled some off the board, and the RC-85 uses these VN10KM FETs. So I noticed that this one is damaged and shows up on our Finercy tester as a resistor. So it's interesting that some of the FETs on the board already look like they were changed because they are the plastic case variant that doesn't have the metal tab like the original ones do. But the original ones here, for some reason, the tester reads them as an NPN transistor. And I was like, isn't that weird? And, you know, just to prove that the tester works, here is another FET that I removed off of the board. So this is another one of the plastic case variants without the metal tab. So this one actually reads good and is a proper FET. We have a VT of 1.72 and RDS on of 2.8. Capacitance is 112 picofarads. So remember those values. So here are some fresh from Mauser VN10s. So I recall Microchip made these. Give me a second while I clean the leads. Okay. So let's get one of the brand new ones in here and see how that reads. And it reads, the VT is a little bit higher, RDS on's a little bit higher, gate charge is lower by like half, so we went from 112 to 50. Let me just make sure here that our where it thinks gate is and source and drain are the same as in the plastic tab version that was already on the board. And yeah. Well, all right. So we'll get our we'll get all new FETs in the board. I also picked up one of these T100 IC testers. So this standalone tester actually handles the chips that our Chip Max EEPROM burner didn't. So let's see here. Alright, so here is the new from Mauser transistor, VN10K FET. So it shows off as an NMOS, drain, gate, source. But if we read one of these metal tab ones that was on the board, so shows up as not found. So it doesn't recognize it. So just for amusement purposes, let's spin it backwards in the socket and try again. So not found on that one. So whatever's going on with the metal tab parts, this tester does not recognize them. And the known good part that was on the board reads right as an NMOS SGD because I had it backwards in the socket. Now it reads as DGS. Alright, so now it's time to connectorize the controller. So I have all the Molex, these are KK.100 spacing connectors. So one's a 14 and one's an 8 pin for logic and audio. These are the .157 spacing Molex connectors here for power and auto patch. So I have all those, but I talked with the client, and we don't really have room on this case to add more connectors because of the way the board is laid out and where components land. It's like I might be able to do it, but don't really think it'll, you know, I don't want to drill more holes and then find out that we've got one hole too many. So spoke with the client, and what we're going to do is the pigtail route. So I picked up a nice beefy DC barrel pigtail. This is 16 gauge, 5.5 and 2.1 millimeter. This is a little coupling, RJ11 on one end. It's only about 6 or 7 inches long though, so that's going to be our auto patch. And for the radios, I'm using these cable to go. These are DB9 extension cables for RS-232. So these are by cables to go, and what I do is I cut them in half. So the female end will go on the controller side, and the male end will go on the radio or the repeater. I also picked up a box of O-rings, which I don't know why they're called the protective coil set, but found one of those that fits the existing hole. It's a little bit ragged, but I think all our cables will fit through there, and we don't have to drill any additional holes. And welcome back. Well, we've connectorized our drops coming into the case, so we do have our pigtails ran. I've also labeled which side is link and which side's repeater. So I was playing with changing the gains on our transmitter audio output because we have way too much cowbell coming out of the controller right now. I also added the tone adjust pot like you've seen in a previous episode. One thing I'm going to do now is add this resistor network to our ULN, where is it? There. Our ULN 2804. So that way we have tie highs on our logic input for COS, link COS, and the PL, because the repeater that's going to be interfacing this is open collector, so we need the tie high resistors so that the controller can see a logic transition. Alright, so this is what we did. We added a 4.7K resistor network, 4 positions, so this covers repeater receiver COS on this pin. Then we have link receiver COS, control receiver COS, and then PL logic input high on pin 4. So the way I did this is when you just want to make a connection, you can just do a solder bridge. Have to play with the spacing a little bit, but you can do a solder bridge and then clear it out when you don't want a tie high on that particular input. Like that. So now I have tie highs on my repeater receiver COS input and my PL logic input. Alright, in our ever-going quest for more cowbell, I have shorted across pins 1 and 2 of resistor network 2, and I also replaced R5. Yes, R5 now has a 100K trimming resistor, so this will be our transmit audio output. So that allows the op amp, transmit op amp, to go into negative gain and then also positive gain if we need it, depending on the position of the pot.
RC-85 V5.2.
And that's about all the time we have for this episode, so as always, thank you for your time and try to enjoy yourselves the rest of the day.